Talking about designing for metal 3D printing. Usually metal additive manufacturing parts are designed for like real life applications and industry, for the fact that they offer great freedom of design, and then it will give you components simplification and decreasing the supply chain complications, and in the same time it will give you an on-demand print, and it can deliver mid-volume parts production as well. Flashback to metal printing. Again, you have your laser being printed, your laser being directed in a programmed way on the surface of the powder, and it will melt the powder and form the layers. Then the base will lower down the thickness of a layer and build the next layer, and so on until you get your final part. The properties that we want to look into while designing for metal 3D printing is the wall thickness. Minimum wall thickness that is needed to make sure that you will have a successful 3D print with this kind of technology should be 0.4 millimeters or higher. You can go with more thinner or finer structure, but depending on the material, orientation, and printer parameters that you're using. For the pin diameter, the minimum wall thickness for the pin diameter, the minimum diameter for that pin should be of 0.4 millimeters. For the hole sizes, hole diameters should be between 0.5 up to 0.6, between 0.5 up to 6 millimeters without any support. If you want to build without any support, like if you want to do holes without any support using this technology, then you can go 6 millimeters and 10 millimeters, but while taking care of the orientation. If you have horizontal holes with a diameter greater than 10 millimeters, then you need support in that case. Escape holes, again, any technology that is doing 3D printing based on powder need some escape holes to be able to clean up any unformed powder out of your design. Then as well, holes are required on hollowed metal parts, as we said, to remove the powder. The bore hole diameter should be 2 to 5 millimeters as a recommendation. If you can create in your design more than one escape holes, that will make your life easier while cleaning the powder out of that sphere. If you have more than one hole, then you can having more options or more possibilities to get rid of the powder inside. Overhanging surfaces. If you have a design that have kind of overhang that doesn't have a support, then you have some limitations. Without doing any kind of support design for the overhangs, then the surface should be 45 degrees relative to the horizon. But it's possible to reduce this angle further by doing some kind of optimization for the laser parameters for the printer. If you have unsupported edges, as we can see down here, these lips, they are unsupported edges. In here as well, kind of bridging, as you remember from before. This is a kind of bridging, this is a lip in here. So if you have that kind of design, then the maximum length of the cantilever style overhanging surface should be 0.5 millimeters. If you have overhanging horizontal surface support, it can be 1 millimeter long. You can apply these kind of rules if you have an extruded or engraved features with unsupported surfaces as well. For the aspect ratio, the maximum ratio between the vertical pin height and the part section is 8:1. So the height relative to the part section should be 8:1. If this height is 8 millimeter, then this thickness should be 1 millimeter. so that you can make sure there's a stability for the printed parts on the build plate. Otherwise it may bend, it may curve, it may fail at all as well. For tolerances, the part tolerances in the print direction could be plus or minus 1 layer thickness. In the XY plane, the achievable tolerance could be plus or minus 0.127 of a millimeters. For the support material, in this kind of 3D printing, you are melting the powder to create a metal. There is a high printing temperatures involved, and there is a kind of layer by layer nature of part construction. So in this case, the support structures are required to connect unsupported geometry to the build platform and act as a heatsink for the thermal energy. So the support performs main roles for the part that is made using this kind of technology. So metal printing melts or sinters the layer of powder at a very high temperature. With that being said, each layer need a kind of something solid to be built to build upon it. Not just only you have just a powder that you can solidify it with laser like the SLS process, but you need for any section that's not attached to the build plate, you need support structure to be printed first, then you have your solid section built on the top surfaces. So just to keep that in mind. The residual stress is a concern as well for this kind of technology, because residual stress is resulting from the differential cooling means, which will make each layer of a metal print needs to curl up or distort. And you need in this case to add support so that you will help drawing the heat out of that layer, so that it will not, it will be sealed down in place and will not do any kind of curving or curling or distortion during printing. As we can see here, this is a metal 3D printed part. Then you can see here the supported materials inside the part. These supported materials need to be removed when you finish your print. The surfaces in contact with support always need a kind of extra post-processing so that you can have a good surface finish of the part wherever the support was needed. So this body in here will be smoother than this one by nature, but you need to have post-processing for the unsupported parts, but mainly for the supported parts as well, with a focus and repetitive process to achieve the smoothness or surface finish that you need based on your application. For the surface quality, sometimes you need design that requires you to have one side of the part to have a smooth surface, which is the side that the people can see. In that case, where you care about the smooth surface finish, then you always need post-processing. If you want to select, if you want to have the part with the surface quality, then you want to take care of the orientation as well. So always you do your part upward facing surfaces. So usually you want to keep in your mind that your part, when you print it, the upward facing surfaces will have sharper edges and will have a better surface quality than the one facing the base of the print. So the greater than angle of a downward facing surface relative to the horizontal, the better the downward facing surface quality. Limitation for this kind of printing technology is the cost. The cost of the metal additive manufacturing machines and the material used are very high. So most likely you will go a lot with the traditional methods of 3D printing because they are more cost-effective solutions. But if you are doing a kind of professional purposes solution, then in this case, yeah, you can go with this method. Design for additive manufacturing. Usually people think that metal additive manufacturing can fit all applications of designs, same as the conventional 3D printing applications or technologies. Like anything can be printed with the FDM, and the SLS can be printed with the metal 3D printing, but that's not always true. If the part was originally designed for the conventional manufacturing, then most likely it will be high possibility that you will fail to print that part with the metal 3D printing. So as we mentioned previously in other lectures, that before you start your design, you want to think what kind of 3D printing technology I'm going to use, and what kind of material, what kind of printer, and what's the limitation for this printer, what kind of capabilities it have, before I do any step toward the design, because your design will change. It will change a bit differently between each 3D printing technology and the other one. Metal 3D printing is considered a complex printer. Usually they are not plug and play. Even the material itself and the applications of it, the way you add it to the printer, all of them need a kind of technical expertise and technical skills. Most metal additive manufacturing machines are industrial in size, and they will be as big as a closet. Then you need to have a kind of controlled operation and material handling, post-processing and maintenance during operation. Most common post-processing methods for metal printing are heat treatment, support removal, machining, and surface treatment. General rules for metal 3D printing: support is critical for the metal printing process, and the geometry, placement, and amount used should be optimized to save time and cost. Part orientation should be kept in mind during design stages. Upward facing surfaces are always sharper, having sharper edges than and a better surface finish than the downward facing surfaces. For the design features, quick overview of design features: wall thickness should be minimum 0.4 millimeters in width. Pin diameter should be higher than 1.5 millimeter in diameter. Hole size: diameter is between 0.5 to 6 millimeters without support. Diameter is greater than 6 millimeters, need support. Escape holes need to be minimum 2 to 5 millimeters in diameter. Overhang should be greater than 45 degrees from horizontal to keep it unsupported. If you have unsupported edges, then the maximum is 0.5 millimeters. Aspect ratio 8 to 1 build height to section width. Tolerances should be plus or minus 1 layer thickness in Z direction and plus or minus 0.1 millimeter in the XY plane. Talking about the designing for binder jetting 3D printing, we mentioned previously, binder jetting is a 3D printing process with diverse capabilities. It can produce functional metal parts, full color prototypes, and large sand casting cores and molds. Binder jetting flashback: you have inkjet print heads, and you have in here, let's change this. So you have inkjet print heads, and you have the part being built in here, and you have the powder bed around it, and then your part will be built eventually by following the program sent to the printer. For the wall thicknesses, if you have a wall thickness similar to this design, the recommended minimum wall thickness is 2 millimeters. This will make sure that the part can be removed from the powder and handled in the green state without being damaged. Again, we're saying the green state. That means even though this part is newly printed and still like warm, and the material is not fully solidified, still kind of green state, not fully solidified, maybe still liquid inside, but it will prevent it from failing during removal from the powder. For unsupported walls like this, whatever called as fins or ribs, it can be great risk of damage for under any kind of axial or especially lateral forces. So it should not be thinner than 3 millimeters in thickness. For the extruded or engraved details, to make sure that these details can be seen and they are not distorted during printing, then you should have 0.5 millimeter below or above the surface, which we see here above the surface, or this thickness below the surface should be 0.5 millimeters at least. For the unsupported edges, again, kind of side fins, we know that, as we discussed before, the powder is all around the part, so it's supporting the part, but unsupported edges are still at risk of breaking during handling in the green state, while they're still not fully solidified. You're handling the part, it could be pulled with something or kicked with something, it could be distorted. So unsupported edges should be no longer than 20 millimeters in length. So 20 millimeters of extruded length up from the original surface. Fillets. Now all fillets should be at least 1 millimeter in diameter. Fillet, we mean about fillet, for whoever don't know about design, when you have a sharp edge like this, then you decide to give it a radius instead of being sharp. And by strength of material, you know, fillet will reduce the stress and strain applied for that corner under loading than without a fillet. So the fillet should be 1 millimeter in radius and should be used in all edges of the design wherever possible. It will make sure that your part will not be damaged in the green state. Edges of the metal parts can be sharpened after inflation or sintering. The radii are particularly important for internal cavities so that it will support in powder removal and accurate construction. For the hole size, to be able to be sure that your hole will be precise in diameter and will not have any kind of distortions or misprints, then you should have no smaller than 1.5 millimeter in diameter hole. Escape holes are important as well, as long as you're using powder. Any 3D printing technique that uses powder need escape holes to get rid of the powder that's still not melted yet. So binder jetting, we know it can produce hollow sections. It works with by sintering the powder, so you need to remove the unwanted powder through an escape holes to let this powder escape with gravity. Escape holes should be minimum of 5 millimeters in diameter, and at least you should use 2 escape holes in one enclosed part. For the feature size, if you have a feature similar to this, then these features can be easily damaged. You can get, with binder jetting, fine details and clear details, but still the material used will be brittle, and especially in the green state, so this could be an issue. So you need to have in mind the minimum feature size of 2 millimeters as recommended. Green state. Out of the printer, binder jetting parts are in fragile green states. So as I mentioned, at this point the parts are very delicate and they're essentially comprised of sand or powder particles that are glued together, so it's easy to be distorted or broken. If the part is very fragile to be handled in the green state, then you need to have a kind of secondary post. Then you can't, if the part is too fragile to be handled in the green state, then secondary post-processing cannot be applied. Usually post-processing will involve a kind of removing the unbound powder from the surface of the part, and with all kind of brushes and pressurized air. So then we'll strengthen the part through an infiltration or sintering steps. So you need to wait until the part is not in the green state anymore, then you do your post-processing, which makes sense, I guess. Then as a designer, you want to be sure to follow the guidelines to ensure that the parts are strong enough to survive the handling during the post-processing. If the feature detail is too fragile, you can add extra bracing structure to the design so that you will improve the stiffness and provide support for that part. These features can then be removed after infiltration or sintering. These are 3 designs about the green state, how you do the best design needed to support the green state from failing the part. This is a poor design. It can easily be compromised and broken or distorted or bent. Preferred design, you have enough support for your hanging part. Optimal design, you have enough thickness, as we mentioned before, 8:1 between the height and the base thickness. So keep that in mind, then your design will be successful and you shouldn't find or face any kinds of troubles during implementation and printing.